All right. Climate change. So uncool. Get it? Because it's hot. Global warming, that is. All right. So on Friday, we are going to venture to Ohio State's campus virtually. And on the west side of campus, there's this phenomenal research center. It's called Bird Polar Climate and Research Center, where there are scientists and researchers that are studying everything from glaciers and environmental change to geochemistry to oceanography and sea level change to paleoceanography, studying ancient oceans, ice cores, and using them to kind of trace geologic change and climate through time. So we have all these different research organizations through Bird Polar. This is from a field trip we took there a few years ago. Gosh, it would have been like 6 or 7 years ago. And there's me wearing some sweet polar gear. We've got some kids there in the ice core freezer. It was like negative, I don't know, something crazy. -4 degrees Celsius in there. I can't remember. So all of those canisters are filled with ice from different parts of the world. And then we have a clean lab. The guy looks like a little alien in there. And what he's doing is he's melting ice and using it to conduct some geochemical studies to look at different isotopes and trapped gases within the ice to use them as a record of atmospheric conditions over time. So to study climate change. All right, so why study climate change? Well, as you guys are fully aware, in a world where we have nearly 7.7 billion people, we are utilizing a lot of resources. And these resources, for better or worse, contribute to changes in the composition of our atmosphere. And so things called greenhouse gases, which include carbon dioxide and methane and water vapor, are gases that trap heat energy from the sun that would otherwise be reflected back into space. And so it creates kind of an unnatural heating. Now, the greenhouse effect is good in the sense that it keeps our planet warm enough to harbor life, but we're getting to a point where changes in temperature are beyond what's natural. And this is where we get into the danger zone for a lot of different ecosystems and people throughout the world. And so this is what Earth from space looks like right now. By 2030, this is what Earth from space will look like at night. And you can see that with all those lights, there is growth in our population. So the estimates are that by 2050, we'll have over 9 billion people on Earth, and all of those people rely on resources, renewable resources and non-renewable resources. Here, the electricity comes from a variety of sources. Most of it is coal and natural gas and oil that contribute to changes in atmospheric compositions. So when we talk about global warming has become really politicized because people don't understand the difference between climate and weather. And so climate is a long-term average of weather conditions. And typically what meteorologists or climatologists will do is they'll take all the data over 30 years and they'll determine the average temperature or the average amount of precipitation, right? So weather, in contrast, is what is happening right now. So from day to day, we get a weather forecast. From decade to decade, or over hundreds or thousands of millions of years, we're talking about a climate forecast. So long term versus short term, okay? Weather is highly variable, and just because we have a warm day, like I remember over the holidays this past year in December, it was like 40s or 50s, 50 degree Fahrenheit, and the kids were outside playing, which is atypical for December in Ohio. That's warm weather. That doesn't necessarily mean that every day for 10 or 20 or 30 years is going to be 50 degrees Fahrenheit in Ohio. So that's not an average of every day, all day for decades, which would be climate. So how do we study climate? Well, CO2 is typically carbon dioxide used as kind of a model for temperature change through time. And there's a positive correlation between carbon dioxide concentrations in the atmosphere and temperature. And we see this particularly in something that's been tracked from the 1950s through today. So we can see this in graph form here. And these graphs go back in time over hundreds of thousands of years. So what I want you guys to observe here, and I'll change it to red so you can kind of see the more drastic change here, is that throughout geologic time, and we're talking 400,000 years ago, back in the Pleistocene, we have had changes in the amount of CO2 in the atmosphere. So there are periods where we have more CO2 marked by these peaks here, and there have been periods where we have less marked by these valleys. And so when we talk about the most recent ice age, which happened here, we see that there's a significant decrease in CO2, which corresponds with changes in temperature. So if you look at this graph and you compare it to the graph below, these temperature variations mimic what's happening with CO2. So when we have a spike in temperature, average temperature, we have a spike in carbon dioxide concentrations in the atmosphere. When we have a valley or a decrease in carbon dioxide, there's a valley or a decrease in temperature. Now, what's wacky is when we get past the most recent ice age into more present day time, we're going to go right here. Let's start here. Around 1880 is kind of the start of the Industrial Revolution. It might be a little bit earlier. I'm not a historian. But my point is that we start to see changes in the amount of carbon dioxide in our atmosphere that are atypical. So 320 parts per million carbon dioxide is high for the last 400,000 years. Right now, as of kind of April, I think we're at 410 parts per million carbon dioxide. And what that means is that on our temperature graph, we are sitting about 1.5 degrees Celsius above average temperature throughout the last 400,000 years. So we're kind of breaking the curve, if you will. So when we talk about the fact that carbon dioxide and temperature kind of mimic each other, the startling reality is that these numbers are historically very, very high. And I say historically, but I mean geologically speaking, they're very, very high. So as far as the greenhouse effect, higher concentrations of carbon dioxide, methane, which is CH4, water vapor, these gases will basically act like a heat sink. So the sun's radiant energy travels through the atmosphere. Some is reflected back into space. Some of it is re-emitted or absorbed by the Earth's surface. And then some of it, like I said, is trapped within the atmosphere. And so what this does, that radiation that's trapped within the atmosphere and kind of re-emitted by greenhouse gas molecules, is what's heating up the planet. All right, so here is the Keeling curve, and this graph is a bit out of date, but this tracks the change in carbon dioxide concentrations over the last 50 or so, 50, 60 years. Right now, we are off the charts. We're way up here. Like I said, about 410 parts per million carbon dioxide. So what that means is if you had a million balloons, 410 of those million balloons would be filled with carbon dioxide. That's what parts per million means. So again, the higher the amount of carbon dioxide in the atmosphere, the hotter the temperature. So our temperatures would mimic this. And there is some annual variation just with seasons, but what we're seeing again is that temperature is climbing at an unprecedented rate. And these temperature changes, this represents average temperature changes. What we're seeing is that in the polar regions, we're seeing even more of a change in temperature. So even greater extremes. The reds and the pinks represent areas where there's been a faster acceleration in temperature. The greens and the blues represent where temperature is a bit more, closer to average. Now, these models are from the United Nations International Panel for Climate Change. These are some of the world's most prominent climatologists that have made forecasts in what temperatures will look like if we continue our practices. And when I mean by practices, I mean like our energy use and the fact that we're using non-renewable greenhouse gas energy sources, what it would look like in the future, meaning like by 2100, as far as average temperature change throughout the world. And so the worst case scenario would be furthest on the right, lower right actually. And this would be a world in which if we continue to do what we're doing now and we don't change our practices at all, and people use non-renewable resources and drive less fuel efficient cars and leave their lights running all day, every day, worst case scenario, by 2080 to 2099, temperatures are changing up to 7.5 degrees Celsius. That's a pretty stark and scary scenario. Best case would be a lot less than that. And so this has an effect not just on temperature, but also on the entire water cycle, and the fact that changes in temperature don't just affect the atmosphere, they affect the oceans, they affect land, they affect the people that live on our planet. And so as the atmosphere changes and it gets warmer, the oceans get warmer, there are changes in the ocean conveyor belt circulation, there are changes in weather patterns, where areas might get more rainfall or other areas might experience more drought. So it's a really complicated puzzle. You can't really take one variable out of it. So how do scientists know what they know about climate? They know what they know because they study ice and they use these proxy measurements or records to provide clues to past climate. And some of those records include ice cores, which we'll investigate with scientists on Friday. Tree rings, you know a little bit about tree rings being a record of growth. Corals can be a record of climate change. Pollen and changes in the biosphere can be a record. Lakes and caves. There's all sorts of different proxies. At Bird Polar, they're studying ecosystems out west as a kind of a proxy for climate change throughout time, changes in biology there. And this is all part of that. They're also studying Western water availability because, like I said, rainfall and drought kind of go hand in hand with changes in climate. And using those as proxies are important because when we talk about resources, water resources are going to be the most significant social issue of this 21st century. And these ice cores can be used to study not just water frozen in ice, but also how climate has an effect on the planet at large. So we can use it to study what's expected to happen in the future. We can use it to study what's happened in the past, and we can use it to model and develop sustainable practices that will hopefully slow what is already a accelerating kind of snowball effect, excuse the pun. But as the earth continues to warm, ice continues to melt, sea level continues to rise, more dark surfaces are exposed, less light is radiated back into space, and it gets hotter and changes the ocean and its circulation. It changes the atmosphere and the weather systems that affect our planet. It changes where areas get more rain or other areas get more dry, drought-like conditions. So it's all this interconnected climate-driven ecosystem called Earth that we need to understand in order to sustain and protect and preserve our planet and its resources. So with that, we're going to meet on Friday, Google Meets, for a live classroom to talk more about what Bird Polar Climate and Research Center does on a daily basis.